So thanks for having the opportunity to present our work, measurement-based transformer modeling approach. This presentation is structured in 4 parts. I will first give a motivation and what our general approach is. Then I'm going a little bit more into deep, what our approach uses, and then how we tested our approach. And at the end, I will conclude and give a short outlook for our further work in that area. Yeah, our work is motivated by the investigation of power transformers under saturation, for example, due to geomagnetically induced currents, GICs. And the question is here, how can we study such a transformer or investigate a transformer as depicted here on the right-hand side, and how to study the interaction with the power grid and the transmission grid. So not only the power transformer, but also what are the effects on the power grid due to transformer saturation. Therefore, we built a digital twin of an already installed power transformer to study the effects on the transformer, but also on the grid. What we are doing is, in general, we use standard information such as the transformer acceptance test, serial sequence impedance, the nameplate information, and with the principle of duality, we transform the magnetic circuit into an electric circuit, which is more common for our power engineers to deal with. And with an on-site measurement where we measure the hysteresis of the core material, we set up the Charles-Edderton model for the hysteresis implementation. And with that, we are deriving an electromagnetic model of the power transformer, which has the advantage that we actually model the 3 different phases with the magnetic coupling. So what we doing here with the principle of duality is, as I already mentioned, transforming the magnetic circuit into an electric circuit for a 3-phase, 3-limb, 2-winding transformer. The equivalent circuit is depicted here on the right-hand side. And with that, we are studying the effects of transformer saturation. And for the hysteresis model, we use a 1-phase measurement setup, as depicted here on the left side of the slide. The outer 2 windings are connected to a power source. We use a low frequency. This enables us to also perform these measurements on site when the transformer, for example, is already installed in a substation. And the 1-phase measurement setup is selected to have a defined magnetic path. Otherwise, if we just measure 1 phase, we would have an inter-phase coupling or magnetic coupling, which would give us different hysteresis curves for the different phases. And we compared this low-frequency hysteresis measurement with standard 50 Hertz measurement, and they are quite well and fit each other. So, and we tested our approach in our lab with a 50 kVA power transformer. We modified them on the high voltage side. We added the neutral point and made all the low voltage connections accessible from outside. So it was a 6-sector transformer or vector group on the low voltage side. We feed all the connections outside. So now we can connect the low voltage vector group to any connection we want to test. And here on the right-hand side, you see the 3-phase current over time, simulated and actually measured. And we see a very well agreement between the simulation and the measurement, and the overall active power loss error between the simulation and the measurement is below 6%. That brings me already to the conclusion. So we have showed and discovered that the simulation and measurements are in good agreement with each other. So therefore, the 1-phase measurement can be used to capture the transformer hysteresis characteristic, and this can also be done with the portable device. And in general, the one-phase measurement gives the same result as the 50 Hertz hysteresis measurement. The model is very fast in computation and power efficient, so therefore it's faster and more convenient to use than FEM model, at least for our case. And as I said, we want to investigate the transformer behavior and the interaction with the power grid. So the focus is not on optimizing the power transformer, but study the behavior and the interaction. And for the next couple of months and years of research, hopefully, we also want to validate the model under DC saturation. So we have 2 of those modified transformers, and we want to set up them back to back and see if that model is also valid for that setup. The next step is then to bring them up to the MVA class transformer and test that approach there. And then also test this approach for 5-limb transformers in the lab and also outside in the substation. So thanks for your attention, and if there are any questions, please feel free.